Wow, forces in action, working hard. Those New Zealand Maori sure know how to compete. Welcome everybody to our Physics 11 screencast. I hope you're all doing well. This is the second in our series on an introduction to dynamics, the concept of forces. So first, let's recap what was addressed in the first screencast. Two main features. First, the ability to use a free body diagram to make sense of what's going on in a situation, labeling forces. And second, as you're building that, to think about the concept of the net force, which is linked to how the object is going to move. So in a bit more detail, that means in your free body diagram, you try to label all forces that you think that are there. Focus on one object in the diagram at a time. Sometimes there's several objects. And as you're drawing each force, try to make sure you're thinking of the length of the vector, how long one should be compared to another, what direction is each force, and if you can, label it with a symbol that represents the type of force, and if possible, even put a number there in newtons if that's given to you in the problem. As you're building your free body diagram, the net force will help inform your intuition if you're missing a force. And there are two things to consider there. So first, if the net force is 0, then all of the vectors should add to 0. The objects would be at rest, they would stay at rest. Or if they're moving, they would keep moving at a constant velocity. In essence, if the net force is 0, the acceleration is 0. The other interpretation here could be if the net force is not equal to 0, and in that case, the object or system of objects would accelerate in the direction of the net force. So those are the two fundamental ideas developed in the first screencast. Let's just see a quick animation of that to make sure we've got it solid before we move on today. So if we take a look at a tug of war, and these two people are pulling against each other, look at the concept of the net force. So let's say they each pull with a force of 500 newtons. Those two vectors are in opposite directions, so they would add to 0. The net force is 0, so there's no motion if they're initially at rest. Their acceleration would be 0. But what if the guy pulled with a smaller force, only 300 newtons, and she continued to pull with 500? The vectors in opposite directions give us a net force of 200 newtons, and they would accelerate to the right. But what about the force of tension in the rope? That's more complex. Well, he's pulling with 300 newtons, and he's pulling along the rope, so that force would transfer along the rope to the woman on the other side. So what would she experience? But she's pulling with 500 newtons, and that force in turn would be transferred along the rope to the guy on the left. So what's the force of tension really going to be? Well, because they're accelerating to the right, if she's pulling with 500, the force against her must be less than 500 newtons, so she still moves to the right. And in his case, although he's pulling with 300 newtons to the left, the rope has to pull with more than 300 newtons in order for him to move to the right. That means the force of tension has to be somewhere between 300 and 500 newtons. And as we progress in our course, we'll learn how to calculate that precisely. At the moment, we're trying to make sure you can develop some intuition, some sense of understanding about what should happen in the problem, as opposed to relying just on mathematics. So those are the two things we've got going forward. Creating a free body diagram is our main way to enter the problems, and then thinking of the net force as we're building the diagrams. Let's add to our toolkit of understanding forces, and in particular how ropes and pulleys influence the forces acting on objects. So let's look at ropes first. If we consider one piece of rope and a person is pulling with 50 newtons to the right while another pulls with 50 newtons to the left, what do you think the force is going to be at the center of the rope? Many students initially think the force must be 100 newtons. But if we zoom in on just that one part of the rope and imagine it's separated and you're holding on to it with your two hands, your right and left hand, because the rope is at rest, the net force would be 0, and that means you're only pulling with 50 newtons on each hand. In other words, the force of tension all throughout the rope is 50 newtons, and it has an action to the right and a reaction to the left in all cases. How about if we take a look in a vertical situation? Well, if the box you see here is at rest, then the force of gravity pulling down must be balanced by the force of tension in the rope pulling up. I've labeled that as Ft1, and you can see it here, it's equal to the force of gravity. Would the tension in the rope be the same all the way up? Well, to be truthful, ropes do have some weight themselves. So as you work higher up the rope is actually supporting more than just the weight of the crate. It's also supporting the weight of the rope below it. That's pretty complicated and is left for more advanced physics courses than ours. So when we're dealing with ropes, we're going to assume that the rope itself has negligible mass compared to the other objects. So in our case, all those three forces of tensions would be the same. Let's take a look at a case where we're pulling horizontally, and the key thing I want you to notice here is we actually have two different ropes. One rope pulling the first block to the right, and then there's a second rope connecting the other two blocks. The force of tension number 1, labeled here in the diagram, is ultimately pulling both blocks and would be a larger force of tension than the tension in the rope between the two blocks. That smaller rope, the one to the left, is only pulling the second block. So those two tensions would be different. But notice within the second rope, the force of tension pulling backwards and the force of tensions pulling forward, that's Ft2, are the same in both cases because it's in the same rope. So when you're dealing with forces of tension in ropes, first, that force of tension is the same in all parts of the rope, and ropes pull in both directions. And second, when you're drawing your free body diagram, it helps to focus on just one end of the rope, where the rope is actually attached to the object. Remember, it's just going to pull on that object. Let's take a look at pulleys. So let's consider a 50 Newton weight that is held by a rope over a pulley. We know there's going to be a force of gravity pulling down at 50 newtons, and if it's held in place, then the force of tension upwards must also be 50 newtons. Now that force is the same all the way through the rope, so you see the 50 newtons on the left-hand side, and that would be the same as the force that we would need to pull with, the applied force pulling on that rope to hold it in place. So the key idea with pulleys is that they change the direction of the force through the rope, but they don't actually change the size of the force. They just change the direction. Okay? So those are the two ideas we're pulling together, that pulleys will redirect a force, and within a rope, the tension force is the same all the way throughout it. And of course, ropes only pull. So, hope that helps as we go forward. So let's take a look at a problem-solving sequence we could use as you're creating your free body diagrams and trying to understand and explain how objects move. We're going to look at an ideal problem-solving sequence. So every step is very clear in the logical process of trying to understand what's going on. Now, by the way, before we begin, as you get a better understanding of dynamics, you'll be able to shorten this process and streamline it. But I think it's best at first to see every step in detail of what's going on. So first, we're going to create a free body diagram, and while we're doing it, we're thinking about what the net force is. Is it zero, or is it in a direction that objects are likely to accelerate? That'll inform your intuition, so you might catch forces you'd otherwise miss. Second, you're always going to be adding those forces together, and because they're vectors, we will have a vector equation that will always be the sum of those forces. And vector equations are always solved using a vector diagram, and you draw your vectors tip to tail. Finally, from your vector diagram, you can apply some mathematical logic to that, whether you're going to add vectors together in terms of their magnitudes or subtract the magnitudes. The vector diagram helps illustrate that. So it seems a bit exhaustive at first, but once you get the hang of these 4 steps, you'll be able to streamline it and do it a little bit quicker as you go. In particular, steps 2 and 3, you can kind of internalize those pieces right away as you see the free body diagram. So our first one, we'll go through it in each step in detail, and then as we progress, we'll be able to go quicker and quicker as your intuition improves. Now finally, when you're done and you have some mathematical logic applied, that should give you the evidence to say that the objects are going to stay in place or accelerate. You're going to be able to predict or explain what's happening in the real world. Okay, so let's model the process with you with a couple of examples. And we'll show all 4 steps at first. Yeah, a bunch of work, but take your time going through as we do, and hopefully you'll understand. We're going to look at pulleys in 2 cases. First, when we use ropes to pull down on a pulley to try to lift a weight up, or if we try to pull up on the pulley, lifting the weight up. To help illustrate that a little more clearly, this is what it's going to look like. So on the left-hand side, you can see we're pulling down on the rope to lift up a 300 Newton weight. Or on the right-hand side, we're going to pull up on the rope to lift the 300 Newton weight. Which one of those two do you think will be easier? Make your guess. All right, we're going to analyze each of those in two situations, just holding the weight in place, and also if we were to accelerate the ball upwards by pulling even harder. And in the process, we'll model those 4 steps of problem solving that we've already discussed. So let's look at this weight that is held in place, and the question is, how hard do we have to pull? Remember, focus on just one object as you create your free body diagram. So we're going to focus on the ball itself. We know that there's going to be a force of gravity pulling down. We've labeled that with a vector downwards with an arbitrary length, and we put a symbol Fg on it. We also happen to know the size of the force, which is 300 newtons. We've labeled that too, and in good form you draw your vectors connected to the center of mass. We know there must be a force of tension in the rope pulling upwards on this weight, so we label it as the force of tension. Now because it's held in place, it's at rest, we know that the net force must be equal to 0, and that can inform our intuition about what's going on. Now step 2 and 3 are the details behind the scenes of our logic. So the vector equation, which is always going to be the sum of the forces in our free body diagram, in this case there's 2, force of gravity and force of tension, we'll then use that to make a vector diagram, and step 2 and 3 are the logic going on in our minds as we're looking at this. The vector diagram, you draw a starting point, we draw our first vector, which is the force of gravity down. Vectors are drawn tip to tail, so the next vector is the force of tension going up. But how long should we draw it? And that's the intuition piece. Think back that the net force is 0, and that means our ending point has to be at the same place as the starting point. So our force of tension vector has to be longer. I'm drawing them to the side just so you can see them more clearly here, but technically they should be right from tip to tail. So the net force is 0, things are looking good, so now we can apply some mathematics to figure out that the force of tension must be the same as the force of gravity. It must be 300 newtons. Now we know that the force of tension in a rope is the same all the way through the rope, so that means that the force that we have to apply as we pull on the rope must be the same as the force of tension, so we must be pulling with 300 newtons of force. So in those 4 stages, the second and third stage were really intuitive. We're just expanding them out in more detail to make it more clear, okay? Let's look at that same situation now, accelerating the ball upwards. How hard do we have to pull now? Again, focus on just one object to draw your free body diagram on, in this case, the ball. So this is a repeat of what you've seen before. This time, though, there's going to be a net force upwards. Again, we draw our force vector right on the center of mass if we can. And our force of tension in the rope intuitively is going to be longer upwards because there's a net force upwards. The vector equation and the vector diagram coming up, always the same, you'll be adding all of the forces together. But the logic behind the scenes in the vector diagram will help your intuition about how large each force should be. So it's the same routine. We've got a starting point. We draw the first vector in our vector equation, which if you remember was the force of gravity. Vectors are drawn tip to tail, so we've got a force of tension vector upwards, but how long should we draw it? We go back to our intuition about the net force. We know there's a net force upwards because it accelerates upwards, so the ending point has to be higher than the starting point. In order for you to see it more clearly, again, I'm drawing the vectors just side by side, but they should normally be drawn tip to tail. Here you can see clearly the net force is going to be upwards. Again, step 2 and 3 are intuition behind the scenes. I'm just making them explicit for our purposes. So we can see here logically the force of tension in the rope has to be bigger than 300 newtons for this to accelerate upwards. That force is the same through all parts of the rope. So just like in the last problem, we know that the force that we apply is going to have to be the same as the force of tension in the rope. So this is going to be harder, which intuitively I hope makes sense. Rather than holding the ball in place to accelerate it upwards, we're going to have to exert a force larger than the 300 Newton weight. Okay, so I hope that's modeled those 4 steps. Let's do them again and see if you can follow a little more independently if we look at the other situation where we have the pulley below us. So, question again, is this going to be easier or harder? Let's find out if you were right. So we focus on just one object. We go through the 4 steps, make a free body diagram first. So we got a force of gravity acting down. The net force is 0 because we're holding it in place. Use that to inform your intuition about what you expect to happen. So a well-labeled free body diagram. We've got the vector going downwards of an arbitrary length, labeled it with 300 newtons. But this time, from the weight's perspective, we have 2 ropes that are pulling upwards. Interesting. Now, behind the scenes again, in our problem-solving sequence is stage 2 and 3, where we do a vector equation, where we add all the forces together. This time we have 3 of them as a vector equation. So now in our vector diagram, we're going to have to draw 3 vectors. So we pick a starting point again. And we've got our force of gravity vector down, just as before. And now I have to add 2 tension vectors to this. Again, the question is, how long should I draw them? Notice they're drawn tip to tail. We go back to thinking about the net force to help us decide how long each vector should be. Here the net force is 0 because we're holding the weight in place. So the ending point has to be at the same place as the starting point. So now we know how long those force of tension vectors should be. So they add back to 0. Again, I've drawn them to the side just to make it clear. So if those 2 vectors combined have to give us 300 newtons of force, we know that each one must have a force of tension of 150 newtons. Interesting. And the force of tension is the same all the way through the rope, yes? And the force we apply will be the same as the force of tension in the rope. So we only have to pull with 150 newtons to lift a 300 newton weight. So this arrangement of a pulley has given us a mechanical advantage. Now, how about if we were to accelerate the ball upwards? Same process as we did in the other situation. Focus on one object to do your free body diagram, just as we've done before. Now, by the way, if you find that drawing your vectors are on top of the object makes it hard for you to see, you can draw them to the side. I've drawn them on top with a white outline so they're more clear to see. We have a net force upwards in this case, so we expect the force of tension in the rope to be larger compared to our last example. And again, we have 2 ropes pulling upwards on the weight. Step 2 and step 3, as we mentioned, vector equation and vector diagram, that's our intuition behind the scenes. We have those 3 forces to combine together in our vector diagram. We pick a starting point, and we draw our force of gravity vector first because that matches our vector equation. I have 2 force of tension vectors to draw. And remember, you draw them tip to tail, so they're right over top of each other. Again, how long should we draw them? Well, go back to the concept of the net force. We're told this weight is accelerating upwards, so there must be a net force upwards. So the ending point has to be higher than the starting point, and that's how we know the 2 vectors are longer. That gives us a net force upwards. Okay, so in our diagram now, we know that those forces of tensions combined have to be bigger than 300 newtons, and that means each force of tension will be bigger than 150. And as before, the force of tension in the rope will be the same as the force that we apply, because the force of tension is the same all the way through the rope. So we know that in order to accelerate the ball upwards, our applied force as well is going to have to be bigger than 150 newtons. Which I hope, again, intuitively makes sense, that you have to pull harder to make something accelerate compared to just holding it. So I hope that's illustrated the 4 steps in that detailed problem-solving sequence. So if you hit something really tough, then slow down and go through each of the 4 stages. But if your intuition is serving you well, step 2 and 3, you can really sort of combine them and internalize them and go right from step 1 to step 4. So making that free body diagram is informed by the vector diagram, thinking of what the net force should be. And then you could go more quickly to the mathematical logic in your diagram. So I hope that's helped illustrate the process for you. You can continue your sample problems in your study guide, see if they're making sense. There is a follow-up screencast to this, part 3, where I go through a few examples for you. Again, non-mathematical at this point, and we still have Newton's laws to develop, but hopefully you can see how the free body diagram really informs what's going on and understanding in a situation. So thanks for your attention. Have a good day. Be well.